as you remember, do a discussion of current algebra. You remember we started this discussion last class, and we had two kinds of discussion last class. The first kind was a discussion of the physics, you know, this model with B field, H flux and an S3 and so on. But what we're going to continue with for a while now is the algebraic discussion. So the algebraic discussion was encapsulated in the following kind of formula: J A J B of Z, this is at 0, my things open up. J A B of Z was equal to delta A B K times delta A B by Z square plus F A B C C J C by Z. Okay, we argued quite in general that this was the case. By the way, you might ask what the delta A B means. In the case of general groups, of course, what it means is the killing form on the algebras. Okay, so I've chosen a basis in which that killing form is diagonalized. Now, if you don't know what this killing form is and so on, at some point in these lectures, maybe in the next class, I will give you a primer on Lie algebra group theory, the parts that we will need for this discussion. But for now, it's sort of intuitive, right? So imagine you were doing SU2. Okay, then delta AB, and we were using the basis J1, J2, J3. Then delta AB is just delta H. Okay, it's the only rotationally, I mean, it's rotationally invariant inner product on this space. It's like a metric. It's like a metric. It's like a metric. More precisely, it's an inner product. Right? It's an inner product on the space of generators. Basically, it's defined by trace in the adjoint representation. Okay, trace in the adjoint representation of the generators gives you a bilinear pairing of two generators. Okay, and that quantity defines the killing form. We'll discuss all this in more. You know, there are two aspects to this study. One is sort of the abstract algebraic kind of things, like are you dealing with a short root or a small, long root? Are you working? What is the dual Cox-Stetter number? You know, all that kind of stuff for general groups will play a role in this discussion. However, the physics of what we're doing is largely captured when we study just SU2. Okay? So today's class we will just study SU2 Lie algebras, SU2 current algebras. Okay? And try to understand a little bit the physics of what's going on. Okay? And in a future class, perhaps the next one, we will study Lie group theory in more generality, remind you of various concepts in Lie group theory, and then try to use those concepts in the more general study of current algebra theory associated with more general groups. Okay? But for today, let's forget about all that jazz that in the end doesn't buy you much. Yes? Yes. Okay, so for today's discussion, I'm assuming we're always dealing with compact groups. Actually, for much of what we'll do in this course, we would be studying compact groups. Okay, and so groups with finite dimensional representations. Okay, it is also true that there exist interesting current algebras for non-compact groups. The most famous of these is SL2R. Okay, because Wesso-Witten theories that give you ADS3 as the target space. Okay, exists just like Wesso-Witten theories that give you S3 as the target space exist. Okay, and the discussion for those non-compact groups is a small modification. I can change the delta AB just to the killing form, and the killing form is whatever it is. Okay, so very little actually changes at this step. When we discuss representation theory, of course, a lot more will change, as is the case even with group theory. Okay, excellent. And you remember that we had taken these guys JA and expanded them. Now let's put these. Maybe we'll put A's and B's up. And we had JAM. So we expanded J. So JA of Z was equal to sum over m j a m of z divided by z to the power m plus 1. The usual expansion. So we had this usual expansion, and then in the last lecture we computed these commutation relations. So we had JAM, JBN, and we got K times delta AB and delta M plus N0. Okay, plus F ABC, ABC plus F ABC, JC M plus N. Okay, so this is this infinite dimensional extension of Lie algebra. So about this, let's first note 2-3 things. The first thing I want to note is that if I set m and n both to 0, okay. Oh, and there was an m here. Yeah, thank you. So if I send m and n both to 0, then I get JA, JB, J0A, J0B is equal to FABC, J0C. And so we see that the 0 modes of these currents are the generators of the Lie algebra. Okay? The non-zero modes are the extension, to give you this infinite dimensional extension. Now, I want to discuss what happens, what we can say about this level K. At the moment, it's just any real number. Actually, with an abstract group, I even have to say how I've normalized my J's to make sense of K. But for now, let's stick to SU2. Normalize the generator so that FABC is epsilon ABC. It's just the usual standard normalization of F. Okay? That removes all normalization ambiguities. Okay? Then this K has meaning. And I want to know what I can say about this K. What I can say about this meaningful K. This convention independent K. Okay? So in your mind now, let A and B run from 1 to 3. We will often use the basis Jz, J plus J minus as usual. Okay? And I want to say something about K. So the first thing I'm going to do is to note the following. Let me take, so let's say J plus annihilates the highest weight state. So I want J plus, J minus plus, right. So let me take the following generators. Let me take J minus and plus 1. Okay. J plus and minus 1. And Jz and 0. Yes. Right now we've specified to SU2. So this Z is, I'll call it J0 if you want. You know, it's the. And then there is one X or Y. X and Y is linear combinations of plus and minus. Right? So, yeah, so we were using the plus minus basis. Okay. So now first let's remind ourselves what the commutation relations are of SU2. So first Jz with J plus, of course, is equal to J plus. This is the statement that J plus carries charge plus. Jz with J minus is equal to minus J minus. And suppose we have J plus is equal to Jx plus I Jy, and J minus is equal to Jx minus I Jy. Then let's look at the commutator of J plus with J minus. This guy, Jx with Jy, gives us Ijz. So we get Ijz, but there's a minus I, so there's a Jz. And this will give us the other thing. So we get j plus with j minus is equal to 2jz. Okay, so these are our commutation relations just for the 0 modes. Okay, so now with this written down, let's figure out the commutation relations for these guys. You see, now I'm doing something new. I'm not looking at the 0 modes anymore. I'm looking at the plus and the minus modes. Okay, so let's figure out these commutation relations. Firstly, j0, 0 with j plus 1 minus. Now let's see. In this case, these two are not equal to 0, so this term doesn't click. Okay, so what we're going to get is something with m plus n, but m plus n is 1. So we'll get something 1. Okay, what we're going to get is from FABC, but that FABC is independent of what this is. Okay, so this will just give us a minus j minus. Remember j0 commutated with j minus 0 was j minus, so it's the same thing with 1, same FABC. Okay, so j0, 0 with j minus 1 plus. Okay, j0, 0 with j minus 1 plus. That once again, similar logic, is plus j plus minus 1. Is this clear? Okay, but now let's look at j 0, let's say, which one was it? Minus 1 plus and j1 minus. First we get the FABC terms. So that is just 2j0, 0. Adding these two. Is this clear? But in addition, we have the terms from the fact that in this case m plus n is equal to 0. So this term clicks. Now I've got a minus 1 here, so I'll get a minus, and I will get this delta AB, which is whatever we got, so that's probably a 2, right? Let's work that out. What is j plus j minus, what is this delta AB? Of course, it's either 1 or 2. I'll just give me a minute. It is G. Okay. So how should we think of this? Just one sec. If we have Ji, Jj, we have delta Ij, and then we just, so it's easiest to just work it out. So it's whatever the clicking we get with using the delta Ij with x and y. So Jx plus Ijy, clicking with Jx minus Ijy, so we get a 2. Right? So we get 2. So we get minus 2. That m was 1 and then k. Minus 2k. And this was plus or minus? This was plus, right? Let's do just. Okay. Great. Great.
Is there a specific reason why the plus 1 oscillator is coming with the j minus?
Actually, there's.
Can I take j minus 1 with the j minus 1 oscillator with the minus 1?
Yeah, you can.
Yeah.
But I've done this intentionally. And you will see exactly why in just 2 minutes.
But the commutation relations will be same.
Will be similar. Will be similar. There'll be some minus sign differences. Okay, but I've done this intentionally for a reason you will see in exactly 2 minutes. Okay, Now, first thing to note about that algebra is that we can massage this algebra into an effective SU2. Okay. So what I'm going to do is going to define J tilde 0 equals J, I think I will define K minus J 0, 0. Listen, then J tilde plus will be equal to J minus plus 1. Okay, and J tilde minus will be equal to J plus minus 1. Okay. Now I want you to stare and see that this obeys the SU2 commutation relations. You see, because I flipped the sign of J0, if I want the SU2 commutation relations, I have to flip the role of plus and minus. That's why I've done this. And adding this extra k doesn't add anything to the commutation relations because k is a constant. But the right hand side works out correctly, and check that it works out correctly with sign, because if we change this around, then it becomes 2k minus j0. Okay, so I've got a new SU2 algebra defined as here. Okay, now Rajat asked why, we could, as he pointed out, we could have done something else, but this will prove convenient, and you will see why. Okay, now in order to examine the implications of this new algebra, in order to understand the implications of this new algebra, the next thing I want to do, in order to understand the implications of this new algebra, the next thing I'm going to do is as far, actually immediately we can see, okay, it will be easier once we go to that. But by the way, one thing we can see immediately from here is that if we want unitary representations, k has better be a half integer. Because in any unitary representation of SU2, all J0 eigenvalues are half integers. Something else that I haven't said but that you already know is that these two operators are Hermitian conjugates of each other, because Hermitian conjugation switches plus and minus just because there was an I, and switches minus 1 and plus 1 just because we're doing radial quantization. The same discussion we had last semester for L's. So these objects are Hermitian conjugates of each other. So we have an SU2 algebra with the standard commutation relations and the standard hermiticity properties. And we know that in any such unitary representation, J0 is a half integer. Right? And so because of that, this k here had better be a half integer. Okay. In this case, we might have wanted to define k, replace k by 2 and write it as an integer. I'll keep it a half integer. Okay. We come back to this in a minute. We come back to this point in a minute. We're going to say it more clearly in 2 minutes. Okay. But we've already learned something quite significant. Okay. And in fact. Let's come back to that. Okay. Now, we've already learned something quite significant, namely that if we want unitarity, this case is not an arbitrary real number, but it has to be discrete. Now let's keep going. Suppose
By the way, if we had taken instead of +1, -1, +2, -2, then instead of 2k we would have gotten 4k.
instead of 2k we would have got 4k.
And then we have to take j0 as 2k minus.
Good point. So if we had done 2, this would also have worked, it's true, and we would have got 4k, and excellent. So you are asking, why doesn't that tell us that 2k is a half integer? That is, k is a half integer divided by, let's say, a quarter integer. Okay, but that's a less restrictive condition than the condition we found here. Right? This is part of the reason that is not the optimal thing to do. We're doing this because this is optimal. Excellent.
But there is an SU2 sitting there.
Oh yeah, there are plenty of SU2s in this thing. Just like in Lie algebra. Take a general Lie group, you can find zillions of SU2 sitting inside. This you're familiar with, right? I don't know how familiar you are with Lie algebra group theory, but a fundamental role in Lie algebra group theory is played by making the SU2 take any root, take the negative root, and take alpha dot h. H is the cartons. We'll go through all this, and you make an SU2 out of that. So just in Lie algebra theory, for every root there is an SU2. Okay, here there are infinitely many. Okay, this is an extension of the structure of Lie algebra with the infinity. Yes, absolutely, zillions of SU2s. Okay, please.
When n equals to n not equals to 0, then what will happen? Like with the algebra?
Well, m is equal to n but not equal to 0, then it's not closing. Because then you get, let's say you took j1, you'll get a j2 on the other side. And then you'll have to include j2, and that'll keep going. What we want to do, there's this infinite dimensional algebra. What we've done is find a small finite dimensional subalgebra. You can always find infinite dimensional things inside. What's interesting is to find small finite dimensional. Is this clear? Excellent. Excellent. So let's keep going. So we have, okay, now in order to really see the power of this, this little subalgebra, what we're going to do is to try to understand the representation theory. Try to understand the representation theory of these algebras. Okay. So now, you remember that when we were studying Virasoro symmetry, we defined special operators such that Tz with O of 0 was like h divided by z square plus del O by z and so on. And we called these O's that obeyed this, we call these primary operators. Okay? These are the operators that have the least singular OPs with T. Descendants have higher singularities. Okay? The least singular OPs with T are those that come sort of from dimensional analysis. There was 1 over z square because T had dimension 2. You can always get more by taking derivatives. Okay? In a similar way, in the study of current algebras, we define primary operators as those that go like this, Ja of z, and now this guy has some group index. Okay? So, suppose we've got a Ti, let's call it Oi of 0. You define primary operators as those that have the OP Ta in representation R, Ij Oj of 0 by z plus da da da. So what have we done? Primary operators, in particular Lie algebra, let's say current algebra includes Lie algebra. So in particular all operators in the theory must transform in representations of Lie algebra. Since J0, okay, J0, you see when we do this kind of decomposition, there that M represents the weight of the operator. J0 has weight 0, okay. So all operators that come into a representation formed from the Lie algebra that is made out of J0s, you understand, right? The zero oscillator number, they all have the same weight, okay. Primary operators have given weight because they have given singularity with this. So primary operators themselves will come in a representation of the Lie algebra, okay. So let's say that this OI, whatever it is in some representation of this Lie algebra. Let's call that representation R. When we do SU2, of course, these representations will just be labeled by J. Okay? These guys are the generators of the Lie algebra in representation R. And they act on OJ like this. This is our definition of primary operators. Let us immediately see that this definition implies that these O's transform under J0 in the usual way. Okay. So the commutator of J0A with OI, commutator of this with OI of Z, okay, is obtained from the pole in the OP. But remember, J0 is integral of J0A is equal to 1 by 2 pi I integral dz JA of Z JA of Z with nothing, because the expansion is JA divided by Z, M plus 1. Okay? And so what we want is the OP of this guy with no extra factors of Z. With so we want the pole in the OP of that, but that was this, which is the usual usual transformation property under representation. Okay, so even if this operator was not a primary, as long as it transformed under Lie algebra in a particular representation, this part, the 1 by Z piece in the OP would be of this form. So we know that the least singular an OP can be for operators that transform under this is to have a 1 by Z pole, because that is what indicates that it transforms in Lie algebra. And that we must have. We define a primary operator as an operator which doesn't have any more singularity than that which it's forced to have. Okay, so this was what its ordinary Lie algebra representation tells you it has to be. And then there's nothing else. Of course, we can get many other operators with more singularity by taking descendants of these. Okay, but the primary is the one with the least singularity. Is this clear? It's very much like Virasoro. Clear? Okay, excellent. So now we've got these nice primary operators. Okay.
But there can be more singular terms?
What? There can be more singular terms if it's not a primary. A primary operator by definition is one that has no more singularity than this.
So this is our definition.
This is our definition, and we will see immediately that if you take descendants of this, for instance, if you act with J minus M, JA minus M on this, okay, that operator, we take a contour integral of JA minus M, this, we will get additional singularities which will come from the JJ 1 by Z square kind of OP. Okay, so you can immediately see that descendants of this have more singularities. Okay. Now, the whole module, you know, just like
In the earlier case, like when you have stress tensor, that expression was making sense in the sense that T acting on some primary will give you some, let's say some coefficient times 1 by z square. That coefficient means some scaling, right?
weight, yes,
Some weight of it. And the other part represents your translation.
exactly.
But here, like, in a sense, I do understand that J is like, T consists of bilinears of J, let's say. So
Yeah.
it should have 1 by Z kind of thing.
Yeah, but the 1 by z, the easiest way to see this is just that J has dimension 1, unlike T which has dimension 2. So if J with O is going to give an O, then you're going to get a singularity 1 by z, just by counting dimensions. Okay? Which is also, of course, the reason why 2 J's can give a T, the Sugawara construction, but we'll come to that. We've not discussed that part. Okay? Right now, just think of it in terms of dimensions. Okay. That, you may wonder, is it possible? Okay, you may wonder, what are the implications of the statement that this operator has only this singularity, meaning no further singularities. Let's understand that immediately. Okay, you'll see immediately in a minute why this is necessary, why it's possible to find such operators, and what their role is. Okay, in order to see that, what we do is the following. Okay, in order to see that, what we do is the following. We take this O, whatever it is, let's say that O has some dimension h. We don't yet know what this dimension h is, okay? But we take this O and we expand it in the usual way, okay? So we expand it as Om by z to the power h plus m. Okay, so O of z is expanded in this way. Okay, and now what I am going to do, is to try to work out the action of, assuming that is the OP, try to work out the action of JAMs on O's. Okay? Okay, so what are we trying to do? What we have here is that OM is equal to integral O of z, and then we want a z to the power h plus m minus 1 dz divided by 1 by 2 pi I. Okay. So that's what our OM is. Okay. So in radial quantization, we make the state corresponding to the operator. Okay, let me just look at the state corresponding to the operator O. Actually, forget all this expansion. Let me just make the state corresponding to the operator. Let me insert O at the origin. I look at the state corresponding to the operator. Okay, and I act on it with JAM. Let me do this action. Okay, so in order to do that, what I have to do is to choose this guy to be JA. Now this was z to the power m dz divided by 1 by 2 pi I. That clear? JA of z. Okay. Then I act on this guy. Okay. So what I'm supposed to do now in this action is look at the OP of J with O and then perform the integral. Because any non-singular term just gives you 0. By Cauchy's theorem. Only the OP can contribute something. But the OP gives us one, so I'm ignoring all factors. The OP just gives us from up there T A R I J O of 0 with Z into Z to the pi. Every other term is non-singular. Okay, every other term is non-singular. And therefore we see that for this is equal to 0 for m greater than equal to for m greater than 0. Okay? For m equal to 0, it's the usual D algebra action. We've already seen that. Okay? And for m less than 0, it's something else. You know, you'll get it by Taylor expanding this O of, we get it by Taylor expanding the less singular terms in the OP, the stuff that we've not kept track of. Okay? That will give us, and that we'll have to worry about later on. The important point I wanted you to understand is this, that JMs with m greater than 0 kilo. Now, JMs with m greater than 0 are negative energy operators, negative dimension operators. Right? Because m measures the dimension of the operator. Minus m is a positive energy, like a creation operator. Plus m is a negative energy. It's like an annihilation operator. And what you see is that these O's are these states that are annihilated by all negative energy JMs. So imagine you're doing representation theory. You're looking for representations of your whole Lie algebra. If there exists a state in this representation that carries lowest energy, then that state by definition must be annihilated by all JMs with m positive. Because if it was not, then JM on the m on that state would lower its energy. So you see that these primary operators O are the operators dual to the lowest energy states in the representation. Now, it could be that in some mathematical way, you look at representations with no lowest energy states. I mean, perhaps that is really relevant for physics. Okay, we're interested in unitary theories, blah, 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 everything has lowest energy things. So at least when you have a lowest energy state, you must have an operator that is annihilated in that representation, then annihilated by all negative lowering operators, and the operator corresponding to that state is the primary operator. Okay? Yes?
That justifies our this definition. Right?
That justifies that.
If there would have been 1 by z square term, then m greater than let's say 1.
You'd have been able to lower it and go down to the primary. Okay? So the primary is like, like a primary in Virasoro. It's the lowest energy state in the representation. All other states in the representation will be obtained by acting on this lowest energy state by raising operators. JMs with m negative. Is this clear? Please.
While the action of J minus x can be figured out by doing that kind of a transformation.
What kind of transformation?
The one where we wrote J treated as in terms of, now there we have the minus component in terms of the 0.
Excellent, excellent. We're coming to almost exactly that point in just 1 minute. Yeah, so, right. Right.
Can it happen that at certain level, by raising operators with negative m, at some level it can annihilate the state? Some thing like minimum models.
Excellent point. Once again, we're coming to just, these are actually the same point. Hang on for 1 minute. In fact, it always happens. This always happens, and I'm going to explain that now. Okay?
But we are not looking at C less than 1 theory.
No,
Nothing C.
no,
C.
no C here. I mean, it's true that there's a C associated, natural C associated with these theories, like the Sugawara construction. That's not C less than 1. And that is not the important part. The connection between the stress tensor and the current algebra, which we will come to soon, is not important for your question. Okay, so both excellent questions. We're coming to both of them. In 10 minutes, if those questions are not answered, please re-ask. Okay, excellent. Fine. Now, you might think this lecture has been completely scattered because I started introducing this other SU2. Then I moved on to primary operators which seem to have nothing to do with that other SU2. And you might think, what's going on? So now I'm going to try to make the connection. So let us remember the other SU2. Okay, maybe it's better to. Let's take it here and rub out everything below it so we can see that. Okay, here you see this other SU2, and what I want to do is to look at the state O, okay, in line with Omgar's question, and look at the action of the other SU2 on the state O. Is this state annihilated by J? Okay, now O transforms in some representation of the usual SU2. Okay, O transforms in some representation of the usual SU2. At the moment, I'll stay. It's one of the states O in that representation. Okay, if you want, we can call it OM. Okay, so let's be specific. Let's say that we have spin J representation. And we've got M such that M goes from minus J to J, just usual SU2. Okay, so say we've got this OM, and that is under the M of the usual SU2. Okay, excellent. Now let's look at the action of J tilde plus on this O. Okay, the action of this J tilde plus on this O, okay, I'm claiming J tilde plus annihilates. Why is that? Just because of the plus one. O was a primary operator under SU2 current algebra. So Jm's with positive M for any M annihilator. Okay? And in particular, therefore, J tilde plus annihilates O because it's J minus, but with some plus one. Is this clear?
So we are taking that particular state, OM, which is an.
It's a primary operator. A state corresponding to a primary operator.
But I thought J minus would.
You see, minus is an SU2 minus. Plus minus ones are the current algebra plus minus ones. And JA for any A annihilates the primary operator as long as M is positive. So that's all we're using. Okay. Is this clear?
So the primary states are like the highest weight states.
Yes.
What
Highest weights for this SU2. Yes.
yeah, this SU2.
For this SU2. Okay. Now, let us look at, okay, let us in particular okay, fine. So this annihilates the state. Okay, what about the state j tilde mine? Okay, first let's look at the other guy. Let's look at j tilde 0. Okay, what is that? That is equal to, of course, k minus, so this, let's say m is the jz weight, k minus m on OM. Okay? And okay. Now let's see this. Suppose this m here was greater than k. Then what we would have is a highest weight state under SU2 tilde whose jz value was negative, which is impossible. Every highest weight state has to have a jz value which is 0 or positive. Okay? So now suppose m was greater than, now, so let's for this problem choose m to be the largest it could be, namely j, to get the most severe constraint. So let's choose m equals j. So we come to the conclusion that k minus j is greater than or equal to 0. This gives us two conclusions. First, that k has to be a positive half integer. We've already seen it had to be a half integer. This tells us it has to be positive, otherwise it's impossible for this to be true. And second, that j has to be less than or equal to k. Okay? And so we come to this remarkable conclusion. We come to this remarkable conclusion that primary operators in a theory with current algebra of level k have to have j less than or equal to k. We've explained this in the context of SU2. There's a similar result. A similar result is true for all groups. Or to even state that result, I will have to review for you all this highest weight, highest root, all that Lie algebraology, which, you know, it's of very little use in real life. But anyway, anyway, I will have to review all that for you. But all the physics is there in SU2. So let's look at SU2. Okay, so in a unitary theory, the representations, the operators have to be in representations that are not too big. Okay. The maximum allowed value for j is k. We will, of course, review all this later, but I'll just quickly tell you the generalization of this to SUN. In SUN, representations are labeled by Young tableau. The generalization of this statement is that the representation, the first row of the Young tableau, which is the largest row, cannot have more than k boxes. Can have k or less than k boxes, but not more. Do you see that in SU2 this is the same statement? Because you see SU2 is just one row in the Young tableau, and then the number of boxes in that Young tableau is j. So j not being being less than or equal to k is a statement for SU2 that the first row of the first row, which is the only row of the Young tableau for SU2, has number of boxes less than or equal to k. And this generalizes very simply to SUN. Okay, more complicated groups, it's more complicated statement. Okay, excellent, 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 excellent. So we have found that this guy, okay, that this guy is, so we found some bound on k. Now let's come back to Rajat's question. Rajat's question was, is there some combination of j minuses that don't, needn't have annihilated the primary, but happen to do so? Let's look here. Let's look at this j tilde minus. Okay? Because in this case, let's continue to act, now just replace this by j. Look at that particular state. Okay, m equals j, this gives us the most severe constraints. Okay? Let us now act, so what was this? This is highest weight state of an SU2 of effective j prime equals k minus j. Right? Because the jz value on the highest weight state was k minus j. And the jz value on the highest weight state is the effective j prime of the SU2 representation. Clear?
Is j, you have said to be 1.
What?
J.
J is any j.
Small j is 1.
What do you mean small j is 1? J is anything. I'm saying, look now, j tilde. J tilde, look for the SU2 tilde. In SU2 tilde, we are looking at some representation. SU2 tilde annihilates this state, this primary state. I mean, it's j tilde plus annihilates the primary state, so the primary state is the highest weight state for SU2 tilde. Okay? Now, the value of j tilde on the highest weight state of an SU2 representation gives you its j, because it's jz on the highest weight state is the j. Right? So, we just have to read off the value of j tilde 0 on this highest weight state and we know which representation we're in. But that value was k minus j. And therefore, when the representation j tilde is equal to k minus j, it's in the spin j tilde representation of SU2 tilde. Is this clear? But if we have the spin j tilde representation, then how many times do we have to lower to get the lowest weight state? Exactly. So what we want to do is, so let's say we were in spin half, we lower once, we get the lowest weight state. Spin 1, we lower twice, we get the lowest weight state, and so on. So what's the formula? Spin 1 we lower twice, spin 3 we lower, spin 3 halves we lower thrice. So 2j minus 1, is this right? To get the lowest weight state? Yeah, this is the number of times you have to lower to get the lowest weight state. 2j tilde minus 1. Spin half gives 1. Spin 1 gives 2, right? Yeah, correct. Spin 2 gives 2. So 2, 2j, you're right. Sorry, 2j, you're right, 2j. What? In order to get the lowest weight state. Yeah. For spin half, you do it once, you get the lowest weight state. For spin 1, you do it twice, you get the lowest weight state, and so on. Okay, so this number of lowerings give you the lowest weight state. So you lower by this plus 1, you get 0. And so we see that j tilde minus to the power 2j, 2k minus 2j plus 1, where I've replaced what j tilde was from here, on Oj is equal to 0. Is this clear? Okay. Now, j tilde minus was j plus, j tilde minus was j plus minus 1. So these were all raising operators. So if you just counted weight, there was no reason for this to be 0. If you just built a current algebra module pretending that all j pluses, j minuses act freely, this would not be 0. But we see here, because of Lie algebra considerations, this is 0. 2k. I've just replaced here j tilde. So it is j tilde, this to the power 2 j tilde plus 1, but j tilde was k minus j. Okay? And so we come to this conclusion that every current algebra representation has null states. These are null states that would not have been obvious from counting dimensions, but are true. Is this clear? Okay. This key point was made in a paper by Gepner and Witten.
What's the name?
Gepner and Witten. Witten's an obscure physicist who you might. Okay. 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 This key point was made in a paper by Gepner and Witten. Now, since we've come to this point, so let's first summarize what we've learned. We've learned many of the key, apart from the Sugawara construction, many of the key ideas of current algebra are already in place. Let me list them one by one. First, there is the OP of the currents. Second, there's the OP of the currents with primary operators. The notion of primary operators, the idea that primary operators have only a 1 by z singularity. Third, the fact that primary operators are lowest weight states. Fourth, that k, which is called the level of the current algebra, is an integer. Okay, now because I used an inner product more appropriate to SO3 rather than SU2, we got half integer. In the fancy way of normalizing, we will normalize things so that this k becomes an integer. That fancy way of normalizing, Jz will be like, there'll be an extra factor of 2. Okay? But with some normalization, some units of conventions, it's an integer. In this case, for SU2, the way we've normalized, it was a half integer.
So the lowering operator will lower by 2.
Lowering operator will lower by 2. You know, the basic difference is whether you allow half integer representations or integer representations. If you only allowed integer representations, then it becomes SO3, and then k would have been an integer. Okay. We'll study that as we go along. We'll do the fancy group theory way, which will give it in a completely general and completely useless way. You know, dual Coxeter numbers, that kind of nonsense. Anyway, okay. But right now, focus on this one example, which has all the physics, all the key physics. Okay, so we've got that this k was an integer that was a positive integer. In this case, half integer, positive half integer. And then, most surprisingly, representations are bounded. Note, this is a very serious bound. For instance, if k was 1, then the only representation is spin half, allowed, apart from spin 0, is spin half. No, not spin 1, because if k was 1, j was less than equal to k, sorry, not 1, k was half. K was the minimum value. If k was half, j would have been less than or equal to half. So spin half would have been allowed. Spin 0 would have been allowed, but not spin 1, not spin 2. So primary operators have to be very simple at low k. The constraint gets relaxed as k becomes higher and higher. Okay? Quite remarkable structure. Quite remarkable structure. Coming only from the requirement. What have we assumed? That there are spin 1 holomorphic currents. That there is a unitary theory. Bas. Coming only from that requirement, we conclude that these primary operators, the representation theory is such that primary operators are very simple. Okay. Now, we have also concluded that there is this null state. Now, every time in conformal field theory, every time that conformal field theory has null states, this implies some equation on correlators. Okay? Every time the conformal field theory has null states, this implies some equation on correlators. And what I'm going to try to do in the rest of this class is follow a Gepner and Witten to extract the content of these of the constraint that comes from this null state. Please.
So let's say that it's this k, level k. Now we have these bunch of different representations, right?
Yes.
Associated to each of these primary, just let's say one primary state. Now my question is, what do these different representations mean in terms of the Verma module? How do these, how are they different? These different representations.
In terms of the Virasoro Verma module or the current algebra Verma module?
In terms of the current,
current algebra. So each of these representations is one Verma module.
No, but the primary state is the same, right?
What do you mean is the same?
Sorry, those are different.
Given a primary, it heads one Verma module. Because you get the representation by acting with all the j minuses on this primary. That by definition is it's the Lie algebra definition of a Verma module. Notice though that this Verma module is never free. Let's introduce this fancy terminology from people who study modules. If you've got a bunch of generators, in this case j minuses, acting on a primary state, you say a module is free if different ways of acting with these generators, different ways of acting with j minuses, give you different states. There is no relation that tells you j minus 1 square plus j minus 2 is equal to 0, something like that. Okay? If you've got a relation like that, it means that the Hilbert space that you're making is not in one-to-one correspondence with all the ways of acting with these lowering operators. We've just argued here that this module is never free. Because this j minus 1 to the sub power is 0.
Not free in the sense it is cutting at some level.
Exactly. There are null states. Another way of saying not free is null states. Okay? But the module, whatever it is this module. The primary is labeled modules. You have different primaries, you have different modules. Possibly you have two different primaries with the same representations. They give you two different modules which are isomorphic as far as Lie algebra is concerned, as far as representations. Clear? Okay, not so different from highest weights in SU2. Each highest weight labels a representation. Could have two different spin j representations. Okay. Actually, but though in some sense, this is even better than SU2. Because in SU2, the number of representations is infinite. Here, the number of representations is finite. Amazing, right? Just totally amazing if you think about it. We've made a much bigger algebra, and then you get fewer representations. Okay. Fine. Okay. Now, what we want to do What we want to do is the following. Suppose I have a correlation function O and then O1 to On. These guys are inserted at Z1 up to Zn. And this guy is inserted at Z. Okay? I want to use the O as a primary operator, O1 to On or whatever they are. Let's say they're primary, but let's say they're all primary operators. Let's say they're all primary. Okay. Now, this is some correlation function. Let's call it G, Z, Z1 to Z. O is a primary operator of O is a primary operator in spin J representation and is the highest weight, is the M equals J component. Okay, let's say that that's the case. Okay. Okay. We have this equation. We have the equation that if we act with j plus minus 1, 2k plus minus 2j plus 1 times, we get 0. But that action is this, is simply this j plus of z times z, no, by z, dz. Right, because we had to do, because we had jm was equal, j went like jm divided by z to the power 1 plus m. 1 plus m, yeah, give me a minute. So if we want just one, we multiply by z to the power m, and in this case m is minus 1. So I think this is right. Right, j minus 1 came with nothing. We want a z to get the pole. Right? So each of these actions is with each of this action is this contour integral on OZ, and then we act it many times. Okay, so we do this, so to say, to the power, what is it, 2k minus 2j minus plus 1 times. Let's say they're primaries. Let's say they're primaries. Okay, very little. We'll see as we go on. I don't even think it will matter. I think it will be more general. But for now, if we need to, we'll assume they're primaries. Okay. Okay. Now we do this. So, okay, this was badly written. This should have been W dW because it's a contour around operator O. Right, so let's look at the diagram. This is Z. There's this contour with W, and then there are many such contours. Okay, and then there's Z1, Zn. The contours are all chosen so they don't enclose any of the other points. Now, the thing I do is the thing we always do. Okay, so let's write out this contour more clearly. Let's write this as j plus w over, this is w minus z, because that's the pole we have to pick out, because we're acting on z. Okay, dw, each of these contours is like that. Okay, and now what we do is to take this contour and deform it and pull it around the sphere. to the other end of the sphere. So it encloses all the other operators. Is that clear?
Sorry, I was not there.
Please, go on.
Yeah, so this J plus was acting on this correlator, or was it just acting on O?
It was acting it was J plus minus acting 2k minus 2j plus 1 times on O.
Just O.
And but we know that gives 0. So I put that equation into a correlation function. So 0 operators, correlators with everything else is 0. So I write 0, which is the action of these on the stuff, and then put all the other operators. Is that clear?
Why is it not acting on the other operators?
Because I want to use the equation that this action on O is 0. That's the equation I have, right? That I act with j tilde minus to the power k on O and I get 0. Right? So so what we have here is that integral, so the thing without these was G. I want to get some algebraic equation for G. Okay? That is my goal, to get some algebraic equation for G. Okay. Now, so what have I done? I've taken this was in a contour like this. I take the outermost such contour and I take it across the sphere to surround everything else. Okay? So I close it like that and I surround everything else. So I come around. So it was like this, I come around and I have this, I circle these guys. So what I will get will be a contour with some minus sign around each of these guys. What is that contour? That contour is j plus of j plus w of w minus z. Okay? But now this w is surrounding times, let's say O1 of z1. Now the contour is surrounding O1. Maybe there's a minus sign because it reverses orientation. Yeah, but let's focus on what's important. Okay? So I take it around here, I act on this. Now this contour is surrounding this. This guy is not singular because now this is a contour around Z1. So this singularity is there's no singularity from here. The only singularity comes from here. Okay, now let's assume that O1 is primary because that will help the analysis. Okay, so since O1 is primary, we know the structure of this OP. Okay, so this is, let's say that these O1s come in some representation I. So O1I we will get J plus T plus Ij Oj of Z1, and then W will be replaced by Z1. Is this clear? And you will have such terms for all of the operators. Is this clear? Now you do it again. Once again, each of these contours goes and hits all of the operators. And then you do it again. Okay? So, and you keep doing it until you've removed all these contours. Okay? So what is the structure of what's left behind? The structure of what's left behind is what follows, is the following. It is that we have T plus, so each of these becomes the action of T on any one of the operators. Okay, so let's call this t plus I, that is in the ith representation, so acting on the ith operator. Okay, sum over I, and then to the power whatever, 2j, what was it, 2k minus 2j plus 1, acting on G, let's say M1 to Mn, these are the internal labels of the group labels of the objects, Z1 to Zn, Z is Z1 to Zn, Z is Z1 to Zn, and then we have these leftover factors. So this t, each t comes with a Z minus Zi, Z minus Zi, yeah, Zi minus Z, whatever. Okay, so this guy to the power is acting on this is equal to 0. Is this clear? Sorry, one last sentence. The important thing about this equation is it's purely algebraic equation. You know, at the earlier point, the equation was some complicated equation involving contours of operators and so on, involving not just the correlator G, but the correlator with extra insertions of J, which was a pain. But now by doing this manipulation, we've had all these J's act on the O's in a way that we know just from Lie algebra. These are just Lie algebra representation matrices.
It's coming from the OP of J with
OP of J. I'm sorry I went fast on that, but that's clear, right? Yeah, and so we get a purely algebraic equation on G's. So it tells us something about these G's, and we have to uncover what. It tells us something about these correlation functions. We have to uncover what it is. Yes, sir.
I thought this summation would come outside
Outside the what?
outside that bracket.
Outside the bracket. What do you mean?
That sum over Ti to the part.
Okay, so we'll have one sum over Ti acting on G, then another one acting on G, then another one, and so on.
Yeah, so summation should be outside, right?
Outside what?
Outside the bracket.
I don't understand. This, let me write this out. This is T1 plus over Z minus Z1 plus T2 plus over Z minus Z2 plus T3 plus over Z minus, say there were only 3.
I thought this T1, these individual terms would be raised to the power 2t minus 2j plus 1.
No, because you see the first guy could go and act on operator 1, the second guy could hit operator 2. You see, the first time you get a contour, that contour folds around each of the other operators.
Yes.
This plus that plus that plus that.
Yeah. Yes. Now.
So see, so this guy was equal to this plus this plus this. Now let's take the second guy. This is equal to the. Now when we undo this, we get a sum of 9 terms where the second guy hits. Okay, one of the terms was the second guy hits this and this. But the second guy, one term would be hits this and this. You see these contours? You could take the contour here. Let me be clear. Take the first contour, move it onto the second operator. Second contour, move it onto the first operator. Such a term exists.
My doubt was coming from the fact that once you, let's say you start with the last contour.
Yes.
On Z, last contour. Then you will end up with all these sum of these individual quantities, right?
Last meaning outermost.
Yeah, outermost.
Yes.
Then you take the second outermost contour, and then what you will get is sum of these two contours, right?
Yes.
All these two contours.
Yes.
So in the end, what you will have is these
If you're saying it's n contours on Z1 plus n contours on Z2 plus n contours on, that's not right. It's the first time gives you n contours. The second time gives you, so okay, so let's imagine that there were only two other operators, just so that we can write it out. Okay, so the first contour will give us T1, T plus acting on 1 by Z1 minus Z plus T plus 1 acting on plus on Z2 minus Z. Okay, this acting on this whole thing acting on O1, O2, O1, O2, and then there's O of Z, which still has another contour around it. Let's say there were two contours and two operators. Okay? Now, for each of these, we get the second operation. When we move the second contour, it can act on this one, which was already acted on by the sum of these two. So that will give us T1 and T1, or this was T2 and T1. This is not clear. I'm saying it very badly. I'm saying what we're going to get is number of operators to the power number of contours terms.
You were saying that the number of contours will get increased by
Each time. Okay, and your counting won't give you that. There will be, if there were 5 operators and 3 contours, there would be terms where all 3 contours hit the same guy. There would be terms where two contours hit one guy and the third one hits us different. There will be terms where all 3 contours hit different guys. Is it clear? Because once you do the first contour motion, it's a sum of terms. And on each of these terms, you do the second contour motion. I feel I'm not saying it very clearly. It's clear? Okay. Okay, excellent. So, what we have achieved is an algebraic equation. Where is our equation? Oh, I rubbed it. Okay, what we have achieved is an algebraic equation. What we have achieved is an algebraic equation for, I've even rubbed it out, but okay, an algebraic equation on these G's. Now we want to understand, what do these equations mean? Okay? We want to understand, what do these equations mean? And the meaning of these equations is quite interesting, but it will take a little time to uncover. So I suggest we postpone that. Okay, what I'm going to explain to you is the following. That I'm going to explain the following things. I'm going to explain that, in general, in representation theory, if you have two representations, let's say J1 and J2, they can fuse to give you anything between J1 minus J2 and J1 plus J2. Clearly, that rule cannot be unmodifiedly correct here, because if J1 and J2 are large enough, then their fusion would give you a representation that has J larger than K. So there must be a new fusion algebra. Sorry. Spence. Huh. Oh, done. Excellent. So when will you get your visa interview? Oh. No, what I mean is the interview didn't happen. Oh, okay, excellent. So when will that interview be? but hopefully you'll get one of those. Perfect. Okay, excellent. Okay, good luck. Yeah. Okay, ciao, bye. Sorry. Yeah. I'm sorry. Where were we? We were. The fusion rules. So this thing is going to tell you that we have modified fusion rules, and the allowed structures that obey these things are going to be are called, in the context of W theory, one usage of this word, are called conformal blocks. In one usage of that term, they form the Hilbert space of Chern-Simons theory with sources on. So we will discuss this in detail without hurrying next class. Okay.
These are like the same thing, the differential equations we were solving earlier also.
Except that these are not differential equations.
Oh, these are
These are algebraic equations. They're completely local. One thing I wanted to emphasize, which I didn't emphasize very much, is that these equations are true for all Z1 and Zn, but also for all Z. Okay. Now, let us see, when is this quantity the largest? Largest it could be. Sorry, it's 1 minute. When is this quantity the largest it could be? It's the largest it could be when j is 0. But when j is 0, the primary operator is just the identity. I mean, one primary operator with j equals 0, so I just identity. Okay? So we could apply this equation by choosing this O to be identity. Okay? This tells us that all these contour integrals acting on identity gives you 0. And then this gives us an equation which is a function of z, but a function of z on a correlator which has identity inserted at z, and therefore is independent of z. So this z is not there, but z is there in the equation. So it's a very powerful equation, because it's a one parameter set of equations true for all z. So we can Taylor expand in z. You'll see. Okay, this part of the lecture is basically taken from Gepner and Witten's paper. And by the way, this is one of these things, it often happens in physics, that the original papers are better than the reviews. This is one of them. Gepner-Witten paper, very clear, reviews mangle it.